Hi everyone, in this video we are going to learn about surface integrals, which are kind of your two-dimensional equivalent of the line integral. So if you recall, what line integral was that instead of integrating over an interval a comma b, we integrate over curves. And here surface integral is somewhat similar, except it is defined in a slightly motivated way, which is that if f is a function of 3 variable, we want to create an integral that gives the surface area of the region if the function is constant. So it's defined in a way, so in sort of like a backward fashion, in the sense that we're starting with the goal that, remember how if your function was 1 for line integrals, you got arc length. So here we want that if we have a constant function that is a constant density distribution, then the double integral should give me the surface area of the region. That's the kind of integral we are trying to find, which we will call a surface integral. So suppose we have a surface which is given in this parametric form, which you are now pretty used to. And this is your parameter domain, UV, right? It's the two-world space. And we break this down into rectangles like you would in a regular integration or finding surface area scenario. And we find the sort of cell that it represents in the vector equivalent. So what's happening, if you recall, any point here, right, gets mapped into a vector, which then collection of those vectors become a surface. And the idea is that when we take the surface integral, we are taking the surface integral over, not over the parametric world over here, but we are taking it over the actual surface. And the idea is, how does that correspond to this particular area? And it has a very close relation to the area of the surface that we found in our previous result. So what happens is we get that the surface integral is defined as a double integral of the function in the parameter r with a factor of ru cross rv, which we saw in our previous videos is, for example, for sphere came out to be a squared sine phi, which is the same as the factor that we get for spherical coordinates. So it's essentially, we are just rephrasing the same thing in a different manner here. So let's look at an example. Compute the surface integral x squared ds, where S is the unit sphere centered on origin. So unit sphere means r is 1, so that my parameters are going to be sine phi cosine theta, sine phi sine theta, and cosine phi. Phi is always between 0 and pi, and theta is between 0 and 2 pi. And we have seen from previous work, we know that UV here, the role of UV is played by phi and theta. So if we take r phi cross r theta and we find the magnitude, it comes out to r squared sine phi. So which case is going to just be sine phi because the radius is 1. So my surface integral x squared ds becomes sine squared phi cosine squared theta times the absolute value or the magnitude of this vector, which is sine phi again, d phi d theta. So we have phi going from 0 to pi and theta going from 0 to 2 pi, and this can be separated out. For theta we have cosine squared theta d theta, and for sine we have sine cube phi d phi 0 to pi. This is an integral we have seen several times now, and we use the half angle formula for this. And it comes out to pi. For sine cube, we'll use a different strategy. One of the strategies for sine cube is to leave one sine phi, rewrite the other one as 1 minus cosine squared phi d phi. So then this becomes two integrals now, 0 to pi sin phi d phi minus 0 to pi cosine squared phi sin phi d phi. This gives us negative cosine phi from 0 to pi. Here we will use, this is the cosine to the m and sine to the n that we've seen long time ago, and the strategy is to set u equals cosine phi. So you get du is negative cosine phi d phi. That's wrong. Negative sine phi d phi. So this becomes 1 to negative 1 u squared, but with a negative du, which becomes a negative 1/3 u cubed 1 to negative 1, which is negative 1/3 negative 2. And this becomes a negative 1 minus 1, which is 2. So we end up with a pi, a 2, and a 2/3, which gives you a 4 pi over 3. Now, once again, this can be applied to surfaces which are given by z equals f of xy or z equals g of xy. And the reason is that these are parameterized as x, y, g, x, y. And we have seen that in this case, again, this is from the previous video, based on the parameters rx, ry, the magnitude of this vector comes out to 1 plus dz over dx squared plus dz over dy squared, which gives us, oh, there's a lot of space here, which gives us the result that the surface integral of xyz ds, if it is parameterized as xy, gxy, becomes a double integral along with this factor of 1 plus dz over dx squared plus dz over dy squared dA. And then, since it's a double integral, you can, if required, move into the polar world and use polar equation or polar coordinate system in order to solve the integral. So all of those tools are open to you. Example, evaluate the surface integral of y ds, where s is the surface z equals x plus y squared, x is between 0 and 1, y is between 0 and 2. So this is an example of where you have a natural parameterization using x and y. So we have dz over dx is 1, and we have dz over dy is 2y. So the surface integral y ds becomes the double integral over parametric domain D, where y is y, because that's the parameterization, and we get square root 1 plus 1 squared plus 2y squared dy dx, which for x 0 to 1 there is no x term. For y 0 to 2 we have a y 2 plus 4y squared dy, and this can be worked out using u substitution. 4y squared giving you du is 8y dy. So y dy is 1/8 du. This gives you a 1. When y is 0, u is 2. When y is 2, you have 4 times 2 squared is 16 plus 2 is 18. And y dy is 1/8. So you have a 1/8 du, u to the 1/2, 1/8 u to the 3/2, 2/3, 2 to 18, 1/12 of 18 to the 3/2 minus 2 to the 3/2. So this is actually 3 so 18 is 9 times 2, right? And okay, let me do this separately here. So you have 9 times 2 to the 3/2, which becomes 9 to the 3/2, and 2 to the 3 halves. 9 to the 3 halves is square root of 9 is 3, and 3 cubed is 27. And 2 to the 3 halves is 2 root 2. So you actually have a 54 root 2 here, minus another 2 root 2. So this is a 52 root 2 over 12, which becomes 13 root 2 over 4, because they both are multiples of 4. Now, just as with line integrals, if S is a piecewise smooth surface, that is, it's a union of a bunch of surfaces that intersect only along the boundaries, then finding the entire surface integral, you can just take all of these different surfaces and add up their surface integrals to get the total surface integral, which means that this process extends to complicated shapes as long as they're only intersecting along the boundaries, which, because these are three-dimensional figures, the boundaries could be planes, or boundaries will be planes. Let's look at such an example. Evaluate the surface integral of z ds, where S is the surface whose sides S1 are given by the cylinder x squared plus y squared equals 1, whose bottom S2 is the disk x squared plus y squared less than equals 1 in the plane z equals 0, and whose top is the part of the plane z equals 1 plus x that lies above S2. Let's draw this. So the bottom part is easy. The bottom is a circle x squared plus y squared less than 1, a disk, which means it's solid. So let's fill it in. But the top part is getting cut by 1 plus x, right? 1 plus x, which makes it this sort of ellipse over here, and then the rest is a cylinder. So that's the kind of shape we're dealing with. And they're giving us these names. So let's use those names. This side is called S1, the bottom is called S2, and then the top is called S3. So which means we have to evaluate all of this stuff for each of the surfaces S1, S2, and S3. So what is surface S1? Surface S1 is the cylinder x squared plus y squared equals 1. Surface S3 is the line z equals 1 plus x. And surface S2 is the is on z equals 0, and it is x squared plus y squared less than equal to 1. Okay, so for S1, first we'll work with S1. Let's use a simple parameterization, which can be used for a cylinder. So cosine theta, sine theta, and z equals z. So what we have here is we need r theta. So r theta is negative sine theta, cosine theta, and 0. And the other parameter is z. So we have 0, 0, 1. R theta cross rz is going to be ijk negative sine theta, cosine theta 0, 0, 0, 1. So I is cosine theta, j is sine theta, and k is 0. Oh, I did have space here. Anyways. Okay, let me move this down here. Okay, so what is the magnitude of r theta cross rz? Is square root of cosine squared theta plus sine squared theta. Same old story, becomes equal to 1. So what is the surface integral for z ds over S1 is the double integral z times 1 times dz d theta. Well, what happens to z? Look at where z goes. Z starts from 0 at the bottom and goes to this surface, which is 1 plus x. 1 plus x in the parameter world is 1 plus cosine theta. And what does theta do? Theta goes from 0 to 2 pi. So we get a half z squared from 0 to 1 plus cosine theta, which becomes 1 half 1 plus cosine theta squared d theta, 0 to 2 pi. And let's see what that becomes. We have 1 half. We are left with 3 integrals. So there will be a 1 d theta, 0 to 2 pi, a 2 cosine theta, 0 to 2 pi, and a cosine square theta from 0 to 2 pi. Some of these are straightforward. First is 2 pi. The second one gives a negative sign, which will give 0. And the third one, again, we have worked with this a bunch of times. It just ends up being pi. So this becomes 3 pi over 2. So the contribution of the surface S1, which is the wrapped around side, to the surface integral is pi over 2. Now the bottom is, we don't even have to parameterize, because for the bottom z is 0. So whatever happens, it's just 0. So it doesn't contribute anything. Now let's look at the top S3. Top S3 z is not 0, so we cannot really use that. What we can do is we can use the natural parameterization, because z is given as 1 plus x. So in this case, we can use the latest formula that we saw. What happens when you have a surface g given as g of xy is you just get 1 plus x, and then you get the square root of dz over dx, which is 1, and dz over dy, which is 0. So 1 squared plus 0 squared dA. And then if required, we will use r cosine theta, and this is just root 2 r dr d theta, 0 to 1, 0 to 2 pi. So you have a root 2, 0 to 2 pi, oh sorry, not separable here, r plus r square cosine theta, 0 to 1, dr d theta, which becomes a root 2, 0 to 2 pi, r squared over 2, plus r cubed over 3 cosine theta, d theta. Well, I suppose when you plug in 1, they become 1. So you have root 2, 1 half, 2 pi, and then a 1/3, which becomes a 0, and a root 2 pi. So net, so the final result will be the contribution from S1, which was 3 pi over 2, contribution from S2, which is 0, and contribution from S3, which is root 2 pi. So you have 3 halves plus root 2 times pi, which is your surface integral. So that's it for this particular video. In the next video, we will learn about what orientation of a surface means, different kinds of orientable, non-orientable surfaces, as well as an application from physics, which is called flux, and look at a few examples. But that's all for this particular video. Thanks everyone.